So we will pick up here on the second day with the integrals of all of the trigonometric functions. There is a link to this on the calendar, so you can print it out if you want to put it into your notes instead of having to write it into your notes, but it's here as well if you'd rather write it in. So on the left-hand side over here, we have all the derivative functions. So for example, the derivative of sine of x is cosine of x, and then over here on the integral side, you can see the integral of cosine is back to sine again. And essentially, they're just going back and forth. So just switching the left and right with integrals and derivatives. And again, typically the ones you'll see most often used are sine and cosine, so you need to know the integrals of cosine and sine. You'll see secant squared used as well, so the integral of secant squared is tangent. These other ones are used, but just not as frequently. So the first three are definite need-to-knows. The last ones are nice-to-knows. But again, as long as you know the derivatives, the integrals should be pretty simple from there. I have this chart up in the classroom. So again, when we derive or find the derivative, we go down the chart. So the derivative of sine is cosine, the derivative of cosine is negative sine, derivative of negative sine is negative cosine, etc., etc. And then the integrals would be going up the chart. So you can use that to help you as you're figuring out problems. So let's take the integrals of these three problems. The first one says find the integral of each of the following, and the first one is the integral of 4 sine of x dx. So remember that 4 is a constant multiple. It just kind of tags along for the ride. If I want to write this correct mathematically, I would pull the 4 out. So I'd have 4 times the integral of sine of x dx. And again, if you look at that chart on the previous slide, the integral of sine of x is negative cosine of x. So this is a negative 4 cosine of x plus c. And again, to make sure that you are comfortable with these and to make sure that you actually believe it, take the derivative to make sure it goes back to what it should. So the derivative of cosine is negative sine, so the negative negative turns into a positive. The 4 tags along for the ride, so we have a positive 4 sine of x. So hopefully that makes sense to you as to why that integral would work out from the problem. On 21, again, we have this constant here of negative 2/3, so I can pull that out. Negative 2/3 is a constant multiple. It does not affect my integral. So it's the integral of cosine of x dx. The integral of cosine is sine, so this is negative 2/3 times sine of x plus c. On number 22, we have a little bit of manipulation to do. Number 1, you'll notice that it's cosine squared instead of just cosine. That should kind of hopefully throw up some red flags in your mind. The integral of cosine squared is not the same thing as the integral of cosine. And in fact, that cosine is in the denominator of the fraction. So that should kind of throw up another red flag because we typically don't have our trig functions in the denominator. So I want to actually rewrite this, if that's okay with you guys. We're going to rewrite it as the integral of 5 times 1 over cosine squared. And I hope that you recognize 1 over cosine squared to be one of our reciprocal functions. And in fact, it is the reciprocal of secant. So this is the integral of 5 times secant squared of x dx. Again, the 5 just tags along for the ride, so I can pull it out. And then the integral of secant squared, if you look at that chart we just wrote down from the previous page, the integral of secant squared is tangent, because tangent's derivative is secant squared. So that's 5 tangent of x plus c. And again, taking the derivative of this hopefully would signal in your head that the derivative would be 5 times secant squared, and that this is just another way of writing 5 times secant squared. All right, let's move on. Again, if you're feeling a little brave and daring, maybe pause the video and try some of these on your own. And then unpause it when you're ready to check some of your answers, or if you need a hint along the way. For number 23, this is a combination of these numbers that are being multiplied. So the 4 is just a constant multiple, the 9 is just a constant multiple. And then we're adding two functions together. So when we take their integrals, we take them individually. So the first one I'll deal with is 4 cosine of x. The integral of that is 4 times sine of x. The second one over here is negative 9 sine of x. Well, the integral of sine of x is negative cosine. So the negative from this integral along with the negative from this coefficient will turn into a positive 9 cosine of x plus c. And again, take the derivative to convince yourself that the derivative of this function goes back to being this function in here. Alright, with this second one, we have some rewriting to do because hopefully you guys, again, don't get confused with all of the different trig functions that we're working with. I'm essentially trying to make it look like one of the integrals from 2 slides ago, or 3 slides ago, actually. So I know the integral of sine, I know the integral of cosine individually, but not necessarily when it's squared or being divided. I know the integral of secant squared is tangent. We also know the integral of some other things, and so our goal is to try and force this function to look like one of those other basic integrals so that we can go forward and essentially take a basic integral. So with this problem, I will do it one step at a time to make sure that you're kind of clear on where everything comes from. So first things first, I'm going to split this up into sine of x over cosine of x times 1 over cosine of x dx. And then that negative that was up there in the top, I'll just pull out front. So I'll put it in the front up there. Sine over cosine is equal to tangent. So this is negative integral of tangent of x times secant, because the reciprocal of cosine is secant of x dx. Hopefully, if you are looking back at those rules, you now know why we did that. I wanted to rewrite it as one of my basic integral rules, and the one that it works out to be is secant tangent, which is one of our basic integral rules. And the integral of secant tangent is secant. That negative out front is the constant multiple, it just tags along for the ride. So this would be negative secant of x plus c. And again, check to make sure that you are confident that the derivative of secant is secant tangent, the negative tags along for the ride, and then if I rewrite this, I can get back to having it as negative sine of x over cosine squared. All I did was split it up into separate fractions and rewrite it using trig rules. Alright, on this last one, number 25, again, we're adding 2 things together, so we'll take the integrals separately. Notice that our important variable in this problem is d theta, so anytime you see a theta, that's our important variable. So we can kind of treat this like x squared. So the integral of that would be using the power rule, like we talked about in the last video. So theta squared would be bumping the exponent up by 1, that's theta cubed, and then dividing by that new exponent. For negative 2 cosecant squared of theta, the negative 2 tags along for the ride, so we have that negative 2 still in there. And the integral of cosecant squared is a negative cotangent. So if I have this negative 2, and the integral of cosecant squared is negative cotangent, that's going to turn this into a plus 2 times cotangent of x plus c. Or actually, sorry, cotangent of theta plus c. Just to reiterate one more time, these rules, specifically the last 3, like the integral of cosecant squared and the integral of secant tangent, while it is important to me that you know how to use them, it's not necessarily important to me that you have them memorized. To earn a 5, I would definitely say make sure that they're memorized, but the first 3, the integral of sine, cosine, and secant squared, are definitely the most commonly used integrals, and so those are the ones you for sure have to have known. These ones might come up on the AP test, they just don't come up very often. Alright, so before we do some more examples and practice problems, I really quickly wanted to address the integrals of our transcendental functions. So the integral of e to the x and the integral of 1 over x. Hopefully you remember that the derivative of each of these, so the derivative d dx of e to the x is e to the x. So if the derivative of an exponential function is itself, then hopefully it makes sense that the integral of an exponential function is itself, e to the x plus c. So you might want to have that one written down in your notes. And then I don't know if you recognize this other one, 1 over x. Hopefully you do, but if not, I just want to address it because people often make a common mistake on that problem. They think it's the power rule, and they rewrite it as the integral of x to the negative 1 dx, and then they bump up the exponent by 1. They say x to the negative 1 plus 1 would be x to the 0 over 0. And I hope that it's obvious as to why that doesn't work, because you're dividing by 0, which means that you're getting an undefined answer. So this is actually not a power rule. So we would not take the integral that way. Instead, this one stems from the derivative d dx of, drumroll, ln of x. Remember, the derivative of ln of x is 1 over x. So the integral of 1 over x is ln of x plus c. So again, these are our integral rules for transcendental functions if you want to jot these down in your notes. Alright, and then the last thing we are mainly going to talk about today is this c value and how to figure out a specific value for c rather than constantly leaving it as an unknown. So, for example, we have talked about how the integral of 4x, here, 4x, the integral of that would bump it up, but we would have a plus c. When we do that and we have that plus c at the very end, what happens essentially is that we call that a general solution. So depending on what my initial condition is, it could change the c value because that c value is just a constant. But if they give you something that they're going to start calling an initial condition, so in this case you guys can see this example back here. They're saying if x equals 0, then y equals 5. That's called an initial condition. It kind of tells you where the graph is located in the coordinate plane, or at least one of the points that it goes through, and that allows you to solve for your constant of integration in order to come up with a specific solution. So general solution is if we leave it in terms of plus c. If we're given an initial condition, however, we're able to find a specific solution. So let's do some examples of what that looks like. So number 18 says solve the differential equation. They give us this derivative, f prime of x equals 3x minus 1, and then they give us this initial condition that f of 2 is equal to 3. So the first thing we want to do is we want to go ahead and take the integral of 3x minus 1. So we're going to say the integral of 3x minus 1 dx is equal to, remember we bump up the exponent by 1, so that's 3x squared over 2 minus 1x plus c. So again, this is called a general solution because we have plus c and we're not quite sure what that constant is yet. And again, this is equal to y. So once we actually find the integral, and technically it's equal to f of x actually. Once we actually find the integral of 3x minus 1, it's back to the original function because it's telling us up here that 3x minus 1 is the derivative. So the antiderivative of that would take us back up to f of x, and here is my antiderivative. That's my integral. So in order to figure out the c value to find a specific solution, we're going to plug in 2, 3 into the function everywhere we see an x and a y. So I'm going to say 3 is equal to 3 times 2 squared over 2 minus 2 plus c. This is called solving differential equations, by the way. Which if you study math in college, there's an entire semester of your college education that's devoted to solving differential equations. If I simplify over here on the right hand side, 2 squared is 4, 4 times 3 is 12, 12 divided by 2 is 6, and then minus 2 plus c. So this is 3 equals 4 plus c, therefore c is equal to negative 1. 3 minus 4. So in order to solve this differential equation with a specific solution, what I'm going to do is I'm going to take my general solution, f of x equals 3 halves x squared minus x, and then I'm just going to, instead of writing plus c, I'm going to write what c is equal to. So since c is equal to negative 1, I'm going to write minus 1. And that is my specific solution. and that's called solving the differential equation. So because we're given this initial condition at the very beginning, we're able to plug that in once we have our general solution in order to find that specific C value. All right, let's try it with number 19. Maybe you want to pause the video and try it yourself, essentially just mimicking the same steps we did in example 18. If I take the integral of both sides, we get that f of x is equal to, and this is just the power rule, so x squared becomes x cubed over 3, negative 2x to the power of 2 over 2, to bump up that exponent by 1, plus 2x, plus c. Everywhere I see an x, I'll plug in 3 from my initial condition. And everywhere I see a y, I'll plug in negative 1 from my initial condition. So I get negative 1 equals 3 cubed over 3 minus 2 times 3 squared over 2 plus 2 times 3 plus c. If I simplify this, I get negative 1 equals 3 cubed is 27. 27 divided by 3 is 9. 3 squared is 9. 9 times 2 is 18. 18 divided by 2 is 9. And 2 times 3 is 6. If I combine some like terms, I get that negative 1 is equal to 6 plus c. And if I subtract that 6 over to the left-hand side, I get c is equal to negative 7. So again, I'm just going to plug that back into my original general solution. So I'm going to plug it in right here. When I do that, I get f of x equals 1/3 x cubed minus, I can simplify that a little bit. I don't have to write 2 over 2. I can just write 1 x squared plus 2x, and then instead of writing plus c, I'm going to write minus 7. Final answer. That is me solving the differential equation. Alright, so we'll do one of these. I don't think it's necessary to do both of them because they're very, very similar to each other. So we'll do example 21. Let me erase this first one. Notice on this one it says to solve the differential equation. The only difference is that on the previous two examples we were given the first derivative and one initial condition about the original function. In this example we're given the second derivative and then we're given two initial conditions. We're given one initial condition about the first derivative and we're given one initial condition about the original function. So essentially we're going to go through this whole process twice. We're going to take the integral one time and find the specific solution for the first derivative, and then we're going to take the integral a second time to find the specific solution for the original function. So if I integrate both sides here, I have that the integral of f double prime would be the first derivative, f prime of x, is equal to the integral of 2x is 2x squared over 2 plus c, which simplifies, by the way, to x squared plus c. Now, I need to use one of my initial conditions in order to find this c value. And because I'm working with the first derivative, then I should use the initial condition that deals with the first derivative. Everywhere I see an x, I'm going to plug in negative 5. Everywhere I see a y, I'll plug in, or an f prime, I should say, I'll plug in 30. So this is 30 equals negative 5 quantity squared plus c. So 30 equals 25 plus c. Therefore, c is equal to 5. And my specific solution, therefore, is f prime of x equals x squared plus 5. Now again, this is not the solution yet, because in order to solve the differential equation, I need to get back to the original function. This is just the first derivative. So let's take our integral one more time so that we can go back to the original function. The integral of f prime would be f of x. The integral of x squared would be x cubed over 3. The integral of 5 is 5x, and then plus c. And now I'm going to go ahead and use that second initial condition that I was given, f of 2 equaling negative 1. And I'm going to plug in a 2 everywhere I see an x, and I'm going to plug in a -1 everywhere I see an f of x, or a y. So this is -1 equals 2 cubed over 3 plus 5 times 2 plus c. If I simplify that, I get -1 equals 8/3 plus 10 plus c. Therefore, c is equal to, let's see, -1 minus 10 is -11 minus 8/3. If I combine like terms by getting a common denominator, that 11 would turn into a -33 over 3 minus 8/3 equals c, which would then lead us to -41 over 3 equals c. So there's my c value. If I put this back in for f of x, I get that f of x is equal to 1/3 x cubed plus 5x, and then instead of writing plus c, I'll just write minus 41/3. Final answer. So go ahead and write that down. Alright, here is our last example for this video, and it's a similar topic, just maybe worded a little bit differently. It says, given that the graph of f of x passes through the point 1, 6, it might not look like it to you yet, but that is an initial condition. They're giving us information about the original function. It says the slope of its tangent line at any point on the graph x, f of x is 2x plus 1. Remember, the slope of the tangent line is the derivative. So essentially they're telling you, hey, guess what? The derivative, the slope of the tangent line is 2x plus 1. And they're saying to find f of 6. So in order to evaluate f of 6, we first should be able to figure out the original function, what is f of x. And once we know what f of x is, we can plug in 6 or substitute 6 into the equation in order to evaluate at that value. So in order to find out what f of x is, let's go ahead and take the integral of both of these sides so that gets us back to the original function. Integral of f prime is f of x. The integral of 2x is 2x squared over 2, which we've seen before, and it always simplifies back to x squared. And then plus 1x plus c. If I use my initial condition at this point, everywhere I see an x, I'll plug in 1. Everywhere I see an f of x, I'll plug in 6. So f of x is 6 times 1 squared plus 1 plus c. If I solve for c, I get 6 is equal to 1 plus 1, or 6 is equal to 2 plus c. If I subtract the 2 over, I get c is equal to 4. So my specific solution is f of x equals x squared plus x plus 4. And again, that's not necessarily what they're asking for as a final answer in this case, but that is an important step in the process. What they're asking for is they want to know f of 6. So now that I know what f of x is, I can come back over here and I can just evaluate. If I substitute 6 into the equation to figure out f of 6, I get 6 squared plus 6 plus 4, which gives me 36 plus 10, which is 46. So the original function evaluated at 6 is the y value 46. And that is the end of this lesson for today.